Have you ever looked up at a massive suspension bridge, a towering crane, or even a ski lift, and wondered, what's holding all of that up? The answer is often an unsung hero of the modern world, the steel cable. And today, we're going inside the factory to witness the incredible process of how these monstrously strong cables are made. This isn't just about twisting some metal together. It's a symphony of engineering, chemistry, and raw power. We're talking about cables that can support thousands of tons, stretch for miles, and withstand the harshest environments on Earth. So strap in, because you're about to see how we turn simple steel rods into the lifelines of modern industry. It all starts with a material you might not expect: high-carbon steel rods. These aren't just any old steel. They arrive at the factory in massive coils, each one looking like a giant metal slinky. The carbon content is crucial. It's what gives the steel its incredible strength and durability. But in this raw form, it's not ready yet. The first step is a process called drawing. Think of it like trying to make spaghetti by pulling dough through smaller and smaller holes. These steel rods are pulled through a series of dies, which are super hard plates with precisely sized openings. With each pass, the rod gets thinner and longer, and something amazing happens to its internal structure. The crystals within the steel elongate and align, dramatically increasing its tensile strength. It's a violent, noisy process, but it's the foundation of everything that follows. After drawing, the now thinner wires need to be protected. Unprotected steel will rust, and for a cable holding up a bridge, that's not an option. This is where galvanization comes in. The wires are passed through a bath of molten zinc at a scorching 450 degrees Celsius. This coats each individual wire with a protective layer. It's like giving it a suit of armor against the elements. This zinc coating not only prevents rust, but also acts as a sacrificio anode. That means if the cable gets scratched, the zinc will corrode first, protecting the steel underneath. It's a clever bit of chemistry that ensures these cables have a lifespan measured in decades, not years. Some applications even use specialized plastic or polymer coatings for extra protection in extreme marine environments. Now we have reels and reels of strong, protected wire. The next stage is where the magic really begins: stranding. A single wire is strong, but many wires twisted together are exponentially stronger. This is where the stranding machines come into play. These are colossal, rotating contraptions that look like something out of a science fiction movie. A number of individual wires, often 7, are fed into the machine. One wire remains straight in the center, forming the core, while the other 6 are twisted around it in a precise helical pattern. This twisting, or laying, is what creates a strand. The lay direction and angle are calculated with incredible precision. This isn't just random twisting, it locks the wires together, allowing them to share the load evenly and giving the strand flexibility without sacrificing strength. But we're not making strands, we're making massive ropes, or cables. So, the process is repeated, but on an even grander scale. Now, the strands we just made become the new wires. These strands are loaded onto another, even larger machine called a closer. This machine takes multiple strands, sometimes 6, sometimes more, and twists them around a central core. This core can be another steel strand, which is common for an independent wire rope core or IWRC, giving the final cable immense crush resistance and stability. For other applications, the core might be made of natural or synthetic fiber, which offers more flexibility and can hold lubricant. As these strands are closed together to form the final rope, a thick high-pressure lubricant is injected deep into the gaps. This isn't just for smooth operation, it's a vital part of the cable's design. The lubricant reduces friction between the strands as the cable flexes and bends under load, preventing internal wear and tear and further protecting against corrosion from the inside out. The sight of this closing process is truly something to behold. Giant bobbins of steel strands, each weighing several tons, spin and dance around a central point, feeding into the die that will form them into the final cable. The noise is immense, and the forces involved are staggering. The entire machine is a perfectly synchronized mechanical ballet, where a single miscalculation could be disastrous. The final product emerges from the other side, a perfectly formed, lubricant-filled, massive steel cable, coiling onto a giant drum. It's transformed from simple rods into a complex, engineered product designed for maximum strength and endurance. It's a testament to over a century of industrial refinement. But how do we know it's strong enough? You can't just cross your fingers and hope a bridge stays up. Every single batch of cable undergoes a rigorous and often destructive testing process. Samples are taken to a quality control lab and placed in a machine called a tensile tester. This is basically a high-tech stretching rack. The machine grips both ends of the cable sample and pulls it with immense hydraulic force until it snaps. Computers record the exact force required to break the cable, which is known as its breaking strength. This figure must meet or exceed the specified requirements for that particular cable. They also test for fatigue by repeatedly bending samples back and forth thousands even millions of times, simulating the stresses a cable would experience over its lifetime on a crane or in an elevator. Only after passing this brutal gauntlet of tests is the batch certified for use. Once the cable is manufactured and has passed all the quality checks, it needs to be prepared for its specific job. This is where the fitting and socketing department comes in. You can't just tie a knot in a 5-inch thick steel cable. The ends need to be fitted with specialized terminals, like sockets, spelters, or eyes, so they can be attached to whatever they're supporting. One of the most common methods is spelter socket. The end of the cable is inserted into a cone-shaped metal socket. The individual wires at the end are then unlaid and splayed out, like a broom. Then, molten zinc or a special epoxy resin is poured into the socket. As it cools and hardens, it permanently locks the wires into the socket, creating a termination that is actually as strong as the cable itself. It's a highly skilled job that ensures a secure and reliable connection point. From the factory floor, these giant spools of cable, some weighing over 100 tons, are shipped out to projects all around the globe. They become the main suspension cables for bridges spanning vast waterways, the hoist ropes lifting containers onto cargo ships, the haulage ropes for mining operations deep underground, and the guy wires stabilizing communication towers against high winds. Each time you ride an elevator, cross a major bridge, or see a skyscraper being built, you are witnessing the silent, reliable work of these incredible steel cables. They are the hidden backbone of our infrastructure, the steel sinews that hold our modern world together. The next time you see one, you'll know the incredible journey of engineering, force, and precision that went into its creation. Thank you so much for joining us on this incredible journey inside the steel cable factory. It's truly amazing what goes into making the things we often take for granted. If you found this as fascinating as I did, please hit that like button and subscribe to the channel for more deep dives into the world of manufacturing and engineering. We love hearing from you, so drop a comment below and let us know what we should explore next. Until then, stay curious.